Chapter 2, Fundamental of Electrical Power. Starting from today, we're going to study Chapter 2, Fundamental of Electrical Power. Chapter 2 contains 8 sections, and today we focus on the first 2 sections, 2.1 and 2.2. Effective value of voltage and current, and idealized component subjected to sinusoidal voltages. Section 2.1, effective value of voltage and current. A sinusoidal current can be represented as a lowercase I represents as an instantaneous value of current, which is equal to Im multiply cosine omega t plus theta. Lowercase I is the current as a function of time. Im represents the magnitude or amplitude of the current. Omega is the angular frequency, and the theta is the phase angle, the units of radians. In power system, we use a lowercase letter for time-varying voltage or currents, and we use capital letters used for quantities and constants. We can see the current waveform shown in this graph. The frequency omega is expressed in radians per second, and the frequency f is expressed in hertz, which means cycles per second. Because each cycle are 360 degrees, which are 2 pi radians. Therefore, omega is equal to 2 pi f. The instantaneous power dissipated by the resistor is equal to the P, lowercase p is equal to I square R. The average value of P dissipated in the resistance is given by P average is equal to the average of I square multiply R is equal to the effective value of current square multiply R. The definition of effective value of current. The effective value of current is equal to the square root of the average value of instant value I, instant current I square. So the effective value of current is equal to the square root of the mean value of the current square. That is also called root mean square, RMS. Now let's derive the RMS value for a sinusoidal waveform. For example, if lowercase v is equal to Vm cosine omega t, the root mean square value of voltage V is equal to the square root of the average value of instant voltage square. Therefore, the RMS value V is equal to Vm, which is the maximum value of the waveform divided by the square root. So the RMS value of a sinusoidal waveform is the amplitude divided by the square root of 2. And this relationship is only applied to sinusoidals. Now let's first look at an ideal resistor subjected to sinusoidal voltage. As shown in the figure, the resistor is imposed by a sinusoidal voltage source. Therefore, we can see, since V, instant value V is equal to Vm cosine omega t, I is equal to V divided by R. Therefore, it's also equal to the square root V divided by R multiplied cosine omega t. What does this mean? This means when a sinusoidal voltage imposed on an ideal resistance, the current is equal to the voltage divided by the resistance. The current is also a sinusoidal waveform. Since the phase angle of the resulting current is the same as the phase angle of the voltage, we say they are in phase with each other. And the RMS value of current is equal to the RMS voltage V divided by the resistance R. The average power dissipated in the resistor is equal to the average of the instant value of voltage multiplied instant value of current, and equal to 2 multiply root mean square value of voltage multiply root mean square value of current multiply the average of cosine omega t square. Since the average value of cosine omega t square is equal to 0.5, 1.5. Therefore, the P average value is equal to the root mean square of voltage multiplied the root mean square of current. So it's the average value of voltage and multiply the average value of current. Now let's look at when a sinusoidal voltage is imposed on an idealized capacitors. So as shown in this figure, when an alternating voltage is imposed across a capacitor, the current is proportional to the rate of change of voltage across the capacitor. So I is equal to C multiplied dV divided by dt. Because V is a sinusoidal waveform, is equal to the square root V multiplied cosine omega t. Therefore, the instantaneous current on the capacitor during this is equal to minus omega c multiply square root 2 multiply voltage multiply sine omega t. Since sine x is equal to the minus cosine x plus 90 degree, therefore the current I is equal to the square root 2 multiply omega c v cosine omega t plus 90 degree. So this means when an AC voltage applied across a capacitor, the current waveform is also a sinusoidal form with the same frequency, but it is a 90-degree ahead of voltage. So let's say we can see this is the current waveform. This is the original voltage waveform. And this waveform we can see is moved to the left side with a 90-degree difference. So we call this as the current is leading the voltage by 90 degrees. And the RMS root mean square value of current I is equal to omega C V. The phase angle between the voltage current, as we can see, is 90 degrees. Now, the average power distributed by a capacitor is subject to a pseudo voltage, since the instant power is a product of the voltage and the current. And so it's equal to the square root 2 multiply V multiply cosine omega t multiply square root 2 I cosine omega t plus 90 degrees. By using trigonometric identity, we can obtain the P is equal to 2 VI multiply 1/2 and the square cosine omega t plus 90 degrees plus cosine omega t minus omega t plus 90 degrees. Since the cosine minus 90 degrees is equal to 0, therefore the P, instantaneous P, is equal to VI cosine 2 omega t plus 90 degrees. Therefore, the average value of a sinusoidal is 0. The average power distributed by a capacitor is therefore 0. What does this mean? This means some of the time the capacitor is absorbing power, which means we charge the current. There's charge on the capacitors, and then sometimes the capacitors is delivering power, which is they are discharging. So the average power is 0. Now let's look at when an idealized conductor is imposed by a sinusoidal voltage. As graph shows, when an ideal inductor is imposed by a sinusoidal voltage, we can see since the instant voltage is equal to L multiplied di divided by dt, so the current flowing along this circuit is equal to the integral of the voltage over time. So it's equal to the L V divided by L multiply V over T. So the instantaneous current is equal to the square root 2 multiply V divided by omega L multiply sine omega t. When we apply trigonometric relationship, the current I is equal to 1 minus omega L multiply square root 2 multiply voltage multiply cosine omega t minus 90 degrees. That means the current will be behind the voltage by 90 degrees. So the current through the conductor has the same frequency, but the current lag voltage by 90 degrees. And the RMS value, the root mean square value of current, is equal to the voltage divided by omega L. Therefore, for conductor, voltage have to be supplied before the current flows. And for capacitor, the current needs to be supplied before the voltage starts to build up. Now let's look at the power distributed by an inductor. The instantaneous power is equal to the instantaneous voltage multiplied instantaneous current, which is equal to the square root V multiplied cosine omega t multiply the square root 2 multiply current and multiply I multiply cosine omega t minus 90 degree. Therefore, the instantaneous power P is equal to V multiply I multiply cosine 2 omega t minus 90 degree. So similar to a capacitor, an inductor also absorbs energies while current is increasing. That the inductor stores that energy in its magnetic field. Then the inductor will return the energy when the current starts to drop and the magnetic field will collapse. So the net power distributed by an inductor is also zero. So the average power of across the inductor is zero. Now we finish the section 2.1 and 2.2.